Here we are, back again, and we're going to start making the transition into some heavier calculus stuff. Let's just recap where we're at. Right now, we're feeling probably relatively good about derivatives. We've got all of our basic function types. We know that with polynomial functions, we're mostly just looking at that exponent rule where we bring exponents out front. With exponential functions now, we've got the rule for how those work. For logarithmic functions, we've got that figured out. We know how coefficients work. They just stick around into our derivative. And we can add and subtract functions very easily. What we're going to do is we're going to come up with a product rule, which is basically going to tell us how to find a derivative of two functions being multiplied together. All four of these examples show function types that we know being multiplied together. So here we've got two polynomials being multiplied. This one, we might just be able to use the distributive property here and start multiplying all this stuff out. We'll get some other polynomial when we do that. We'll keep going, and we could find a derivative that way. But for all these other function types, x e to the x, x minus 3 ln x, x cubed, log base 5x, when we have these different function types being multiplied, we can't just use algebra to simplify it and write it in terms of something that we know. So for at least these last three, we'll have to come up with a rule that'll tell us how to find the derivative of these things. The easy mistake that people will make is they'll look at something like x e to the x and they'll say, all right, here, this is going to be the derivative of x times the derivative of e to the x, which would be 1 e to the x or e to the x. Really easy for people to say a product of things, just find the derivative of each and multiply them together. That's not going to work. I'll show you pretty quickly of an example that we can show that that won't work. That's going to be the easy mistake that people fall into. Don't do that. So here's our leading example. The nice thing about this example is that we can just multiply this. 3 times 4 is 12. X squared times x is x cubed. This is really 12x cubed. So in the back of our heads, we should just know that the derivative of this function here is really 3 times 12, and then we'll lower our exponent by 1. 36x squared. Now, if we go ahead and we try the wrong approach here, we could say, all right, f prime of x is equal to the derivative of 3x squared, that's 6x, times the derivative of 4x, that's 4, and you'll notice we get 24x. That's not what it's supposed to be. It's supposed to be 36x squared. So we're going to have to come up with another way of getting to that. And what we could do is start labeling these things. Maybe we'll just say, like, here we've got 3x squared here, we've got 4x here, and we've got the derivatives of each as well. And we can notice that we want to get something with an exponent of 2. And so if we start putting some of these things together, you'll notice that certain combinations will give you x squareds. For instance, 3x squared times 4 gives you 12x squared. So the exponent's right, but our coefficient is messed up. So maybe we could try the other pair. 6x times 4x is 24x squared. So we've either got 12x squared or 24x squared, and both of those are wrong, even though the exponent is correct. You can notice pretty easily that if we add those things together, though, that'll give us our derivative. So if we look at 3x squared times 4 plus 6x times 4x, that gives us 12x squared plus 24x squared. There's our 36x squared that we knew we were supposed to get. Now in this example, it's not a very good example to use this product rule because we can just multiply it out. But our product rule is going to be something that will help us out when we can't multiply these things. What we're going to do is we're going to call these two things a function u and a function v. And then we'll notice that we can combine those and their derivatives. This would be u, this would be v, this would be u prime, and this would be v prime together to get this derivative of the whole thing. So to summarize all that stuff, here's our product rule. So we're going to say that u and v have to be differentiable functions, or they're at least differentiable at the point we're looking at. And f of x is u times v, the product of these two things. Then f prime, or the derivative of this whole product, is u prime of x times v of x plus u of x times v prime. Now, a lot of times we'll just shorten this. We'll drop off all the of x's. We'll pretend that we don't really care about the function notation, which we don't really, and we'll just write it this way. So all we really have to do here is identify our pieces. We'll call them u and v. You can really call them whatever you'd like. It doesn't matter. And then we'll find the derivatives of each, and if we go backwards, we'll do this little crisscross thing. So this is what our work will look like. We'll say u is equal to something, v is equal to something, u prime is equal to something, v prime is equal to something. We'll multiply those pairs together and add things. That's our product rule. So let's take a look at the 4 examples that we had at the very beginning. Again, this one, we may as well just multiply everything out here, but just for our own sake, let's get some practice with this. So here, I'll say that u is that first piece, 4x cubed minus x squared plus 1. And v is going to be x squared plus 5x minus 1. Now, u prime is just the derivative of this. So 12x squared minus 2x, and my constant goes to 0. We should be very comfortable with these. V prime is the derivative of this, so we'll say that's 2x plus 5, and again, that constant goes to 0. And I always draw my little crisscrossy thing in here. So now I can start writing out what f prime of x is. Notice it doesn't actually matter what order you do this in. We could do u and v prime first, or we could do u prime and v first. We're just going to add things up. Since addition is commutative, it doesn't matter the order. We can do this in however way that we'd like. It doesn't matter which of these you pick as u and which of them you pick as v. So I'll just grab the pairs. I'll say, all right, 2x plus 5 times 4x cubed minus x squared plus 1 plus 12x squared minus 2x times x squared plus 5x minus 1. And now there's just a bunch of multiplication that we'll do. So there's a lot of algebra here. So we've got 8x to the 4 minus 2x cubed plus 2x. That's 2x multiplied by all this stuff. Now I'll multiply 5. That's going to be, that's going to be 20x cubed minus 5x squared plus 5. And now I'll do all these ones. 12x to the 4 plus 60x, x cubed. That's 12x squared times 5x minus 12x squared minus 2x cubed minus 10x squared plus 2x. And now we just have to put all this stuff together. So I've got 8x to the 4, and I've got 12x to the 4, so that's 20x to the 4. Let's see my x cubes. I've got a negative 2 plus 20, so I'm up to 18. Plus 60, so that's 78, minus 2, so that's 76. And then my x squareds, minus 5, minus 12 is negative 17, minus 10 is negative 27, x squared. All my x's, 2x and 2x, is that it? Just plus 4x. And then lastly, my constant, plus 5. All right, so double check all that, I guess, because I can make stupid little addition errors a lot. But that should be our derivative here. Notice the hard work is after this first line, multiplying it out. Most times, the product rule isn't very helpful to do with something that we could just multiply this out originally, because then we just have to multiply it once, and then the derivative becomes easy. You'll notice that it'll go a lot quicker with examples like this. Here, maybe I'll stop and I'll let you give a shot to this one. So hit pause on the video, give this a shot. I'll set up my U's and V's, and you can come back in a second. All right, if you're back here, we've got x and e to the x. The derivative of x is 1. The derivative of e to the x is e to the x. You're going to do this, so go ahead and do that. All right, so f prime of x is going to be x e to the x. That's our u v prime, plus u prime v, that's just going to be 1 e to the x. Now, sometimes you'll see this factored. There's a common factor of e to the x here, right there, and right there. So we'll pull that out, and we've got e to the x times x plus 1. Now, I don't care which one of these you give me. I'll take both of them. But on like multiple choice stuff, you might see this as an answer, and so you'll have to notice that, oh, okay, it's just a factored version of it. But that's the derivative of x e to the x. Not so bad with functions like that, right? All right, give a shot to these two. I'll set up the u's and the v's for both. That way you can kind of make sure everything is settled in before you start it up. Or if you want to start it now, go for that too. We can call this x minus 3, and the derivative of that's just 1. V is going to be natural log x, and the derivative of that is 1 over x. And for this one, u is x cubed, and v is log base 5 of x. U prime is 3x squared, and for v prime, we've got 1 over x natural log of the base 5. All right, give these a shot, see what you can do. All right, multiply some stuff out. So I've got x minus 3 times my v prime here, 1 over x. So I'm going to say x minus 3 over x. I could write it out as multiplication, but I'm just going to put it at that fraction. Plus 1 times natural log of x. There we go. Now, if you want, you could notice that there's that upside down triangle here. That shape of that fraction, so that means it can be split up. So this is really x over x minus 3 over x plus natural log x, or you could say 1, or you should, if you're going to do this, you should say 1 minus 3 over x plus natural log x. And that's our derivative. I'd also take this if you wanted. That's fine. Either of those is good for me. Every now and then you'll see people multiply this together, or sorry, add these two things together. So maybe we could do like common denominators. We could say like x minus 3 over x plus x natural log of x over x. And so you have x minus 3 plus x natural log of x over x. You could do something like that if you wanted as well. Lots of stuff to do. All right, here we're going to do our little crisscross multiplication. I forgot to draw it in here. There we go. Crisscross multiplication here. So let's see what we've got for the derivative of this one. I'll start with these ones because it doesn't matter what order I do it in. So 3x squared times log base 5 of x. Good for me. Plus x cubed over x natural log 5. So we can say 3x squared log base 5x plus, notice the x's can cancel. So this is really x squared over natural log 5. And then if you want, you could rewrite this using the change of base property. And so you could say that's really 3x squared natural log x over natural log 5. Natural log x over natural log 5, that's our log base 5 of x. Plus x squared over natural log 5. And now you've got something like x squared times 3 natural log x plus 1 over natural log 5. I just added these things together and factored out my x squared common factor here. So you could do something like this, or if you wanted, you could just leave it this way as well. So either of like this one here or something like that would work. There's not a lot that we can do with these logarithms to make them look nice, but that's how the product rule works. So again, don't fall into the trap of looking at the derivative of each of these pieces and just multiplying the derivatives together. You're going to multiply the derivatives by the other function, and vice versa. So one function goes with the other derivative, the first derivative goes with the other function. So keep that part in mind, this little crisscross thing. Try and stay organized when you're labeling everything. I like to put it off to the side just to make sure I can see what all my pieces are. But as long as you stay organized and don't fall into that trap of multiplying derivatives by derivatives, you should be good. There's not a lot that we've got to do here.